I want to explain how one-slit interference leads to an interference pattern on a wall that looks like the absolute value of the sinc function. Okay, first of all, here is the sinc function, but it doesn't really look very good like that, so let's multiply it by 2 pi x, and so we can get a better idea of what it looks like. It goes up and down and up and down and up and down, but you get a big peak in the middle, and if I put absolute value signs around it, then all the negative lobes become positive lobes, and it looks like it bounces up, gets bigger until it reaches a peak, and then it gets smaller again. So that is what the function looks like. It is notable that when you get to this 0 point, it's technically undefined, sine 0 over 0. Um, but the absolute value but really the 0 over 0 and the limit becomes close to 1. So it just uh, looks like a pretty um, even graph. We want to make a distinction here between what the interference pattern actually looks like and a, a graph of the intensity of the interference pattern. What you'll actually see on the screen, of course, is not the graph of its intensity. You'll see it bright spots where the intensity is high and dark spots where the intensity is low. So now let's look at what happens in the one-slit interference process. We have this light coming through a slit in a wall, and this light is projected onto a screen. What you would see on the screen is a pattern of light and dark spots. Between this red dot and this green dot here, there could be several wavelengths. Let me move that over so you could see. Here's 1.75 wavelengths. And over here is the contributing electromagnetic waves to this point here. When there are uh, more peaks than troughs, or more troughs than peaks, we have light. Right here we have a peak, and then I move over here. We've still got a peak, but it's not as big as it was. And then I move over here, and now we've got some area of troughs. So these red areas subtract from the orange area. And here we have the red area and the orange area are equal, so the two completely cancel out. Um, the amount of light is proportional to the area of the lobe that is not canceled. So if I move over here, we have two red peaks and one orange peak. So what's left over after things are subtracted is one red peak. So that the height of that curve there is equal to the area of one of those red peaks. We can change the number of lobes contributing to this spot by moving the point on the wall. So there is a different amount of electromagnetic intensity incident on each point in the wall. Now, something interesting about this, if you've ever heard of the Fourier transform, you might be interested to learn that the mathematics of a single slit interference is identical in some ways to the mathematics of the Fourier transform. In particular, the single slit can be represented by a rectangular function. From like here, we've got this integral from negative w to w, and that's essentially representative of, and basically I would put a 1 in here. So negative w to w and multiplied by 1, that is something called the rectangular function. And the interference pattern shows up as the Fourier transform, which is just multiplying. Usually it's e to the power of ft dt, or e to the, sorry, imaginary ift but here I'm just using cosine. Anyway, uh, the single slit can be represented by the rectangular function, and the interference pattern shows up as the Fourier transform of the rectangular function. And, um, we can kind of do that as well with two-slit interference by, instead of using the rectangular function, we do a tiny little slit over here with w minus d to w plus d, where d is 0.05, and then also another slit on the other side so that the d is 0.05. And then we get two-slit interference from this graph here, which you can't really see here, but it does, it looks like it keeps going strong, but if I zoom out a long ways, you can see that it starts petering out after a while. But two-slit interference doesn't peter out nearly as quickly as one-slit interference. Another interesting property of this result is the relationship between momentum and position. You might notice that by passing a photon between or into this slit or through this slit, that it has constrained the known quantity of its position in the x direction. And now that we've constrained its position in the x direction, the its trajectory becomes, to some extent, unknown. And most likely it will land right here in the middle of that, but it might end up in any of these other locations as well. We could, in principle, calculate a standard deviation of all the possible places the photon could land, multiply it by the uncertainty in the place it passed through the slit, and the product of those two quantities has a minimum value, and the minimum value is described by a principle that is known as Heisenberg's uncertainty principle. Basically, that the change in, or the uncertainty in position times the uncertainty in momentum is greater than a certain value related to Planck's constant. This Heisenberg's uncertainty principle is also the limiting factor determining the resolving power of a telescope, though in that context one uses a big circular mirror instead of a narrow slit, and the concept is usually described by the words the Rayleigh criterion.